Okay, irrational numbers, non-perfect squares. Here are notes for irrational numbers and non-perfect squares. So, essential question, how can a square root of a number be calculated when it's a non-perfect square? So a perfect square is like 1 by 1, right? 2 by 2, right? So how many is 2 by 2? 4. But if you do 3 by 3, you get 9. Yes? So in between these numbers, 5, 6, 7, and 8, we're talking about the non-perfect squares. It's somewhere between 2 and 3. It's more than 2, but less than 3. Let's talk about a concept here. When we were doing the exponents, we talked about relationship between base and exponent. You know, something raised to the something power. This is also the same thing. It's about that relationship, and it's about writing things in a different way. So it's about simplification. This will simplify. This is a tool we use to simplify math going forward. And it's a very necessary tool when numbers get what you think what? Really, really large and really, really small. When they get crazy small or crazy large, we need to simplify those numbers and have a method to shorten them. Okay? And to do that, we need to have this sort of relationship between the base and the exponent. Okay, question number 1, what's a perfect square? A perfect square is any factor or base. Remember, we call that large number at the bottom the base. Raised to the power of 2. That's what it means to be squared. It's the same number times itself. Okay? So example, 4 squared means 4 times 4 or 16. I want to take a moment and point out this is the computer symbol, and sometimes on your calculator for an exponent. So if you see a number, that's the base. That tells the computer that the following number is the exponent. And that's important not just for using like Excel, which you'll have to start, using as you get older, but also in some calculators, they really want you to use that little caret thing. And it's also on calculators. You'll see it on calculators. Okay, next slide. Oh, our model. So I know this looks rectangular, but if we did 4 here, meaning it's 4 up and down, and we did 4 across, how many little squares does it make up? 16. Okay, so 4 squared equals 16. It's a little bit more defined there. Okay, question number 2. How is a square root of a perfect square calculated? So we calculate the square root using the model. Focus on the base of the square, or what factor when multiplied by itself would give you that number. So in case of 16, you know that 4 times 4 is 16. You guys know perfect squares already because they're just a part of learning that 12 by 12 multiplication chart. You know that 144 is produced by what? 12 times 12. You know that 64 is produced by 8 times 8. You know that 49 is produced by 7 by 7, right? So you guys know perfect squares pretty well. But the idea of a square root it may be new to you. So this symbol, this funny division sign thing with the check mark, is called a radical. And it tells you that whatever is inside that radical, you're going to find a more simplified base power for it. So we use that to convey maybe a larger number or something that we don't want to write out. Okay, so no, this known as a radical is used to find roots, cube roots, etc. Before we go to question 3, that is equal to square root. Okay? If you see this, that's equal to the cube root. So for example, the square root of 25 is equal to 5. The square root of 25 is equal to 5. The cube root of 125 is equal to what? 5 times 5 is 25. 25 times 5 is 125. So 5 is the cube root. I'm sorry, you can't see that. Okay, add this to your notes. The square root of 25, this is the square root. It's implied that it's to the second power. But if you see it and it's got another number up here, like the 3, that means the cube root. Or what to the third power gives you 125, and that's what it's equal to. So you did this with, give me another one that we did like in our warm-up, where you took something to a higher power than just squared. 7 times 7 times 7, 7 to the third power. Now that's not 7 times 3, right? 7 times 3 is 21. 7 to the third power. Okay, so 7 times, what is that? 7 to the third power. Okay, 343. So 343 is equal to 7. The cube root of 343 is equal to 7 because it's equal to 7 times 7 equals 343. So that's just an example of how you use a different power. Okay. All right, let's move on. You ready? All right, flip the page. No? Okay. We can come back after we finish the notes. All right, question number 3. What is an irrational number? An irrational number is a number that cannot. An irrational number is a number that cannot be written as a ratio. Can't be written as a fraction. It won't be perfect. It won't be accurate. Okay? It won't be accurate. It might be close, but it's not accurate. We can't accurately write it. Okay? All right, did I miss that? Okay. Okay, so question number 4, how is a square root? Okay, so how is a square root of a non-perfect square calculated? So a non-perfect square are those that we gave examples of earlier, like the square root of 5 or the square root of 6. Those are non-perfect squares. Okay, so non-perfect squares are irrational numbers. But we can use approximation strategies to calculate those values. The purpose, listen, the purpose of this whole thing is to approximate imperfect squares. Not to be like exact to like the third or fourth decimal. There's no rule. The purpose of this mostly is that you could say order them in a specific order where you would know where they go. Are they bigger than this or are they smaller than this? So I might say the square root of 5, is it bigger than 2? Or is it bigger than 3? What is the square root of 4? 2 times 2 is 4, right? So the square root of 4 is 2. So the square root of 5, therefore, is that going to be bigger than the square root of 4? Yes, it's going to be more than 2. Okay? All right, so here's the looking at the radicand. That's the number inside the radical. Identify the two perfect squares that it lies between. So for the example of looking at the square root of 5 is in between the square root of 4 and the square root of 9. We know these, right? What's the square root of 4? 2. What's the square root of 9? 3. So which do you think it's closer to? 2 or 3? 2, because 5 is really close to 4. It's a lot closer to 4 than it is to 9. Okay? Look to see which it's closest to. We said it was, in this case, it was closer to 2. And if it lies between both, if the answer to the radicand lies between both square roots, make your best guess. It is about estimation. Okay. All right. So let's do this example before. So the square root of 16 is 4, but the square root of 18 we need to estimate. So here we have 16, 17, 18, 19, 20. What's the next number up from 4? 5. What's 5 squared? 5 times 5. 25. 21, 22, 23, 24, 25. So the square root of 25 is 5. The square root of 16 is 4. And we're looking at the square root of 18. So do you think the square root of 18 is closer to 4 or closer to 5? 4, right? Because this is like right in the middle, isn't it? So this is about 4.5, yes? You got 1, 2, 3, 1, 2, 3, 4. Okay, so 4.5 is probably somewhere in here somewhere. It doesn't have to be exact. It's about estimation. Does that make sense? So you'd say the square root of 18 is probably about halfway between 4 and 4.5. And that level of estimation is probably more precise than you'll ever need. Okay? So don't freak out. Sure. And that alone will probably give you all the answer you need. Okay? All right. Let's pause the. Okay. So before we move on, here are the answers. 36 is a perfect square. 144 is a perfect square. But the square root of 45 and the square root of 105 are not perfect squares. Okay, they would be between, square root of 45 is between 6 and 7, and the square root of 105 is between 10 and 11. Okay, let's move on to our sets and subsets section. This is from the vocabulary from last week. So organizing all real numbers into a Venn diagram. Okay, so we have over here, if you want to just draw like a circle, these are all the real numbers. There's a little section over here we're going to save for irrational numbers. So everything on this side of this circle are rational numbers. So does anybody have an example of an irrational number? There's one really famous one you've learned about so far. No, 0 is actually doesn't count in that. It's nothingness, yeah. Pi. See, because we can't write an irrational number exactly, that's why it's irrational. It doesn't make any sense. We can't write what it is as a number. That's what. Okay, sets, subsets of real numbers. So if you look at the Venn diagram over here, we can just put this over here, and we're going to put our irrational numbers over here. Now our main example, our main example of irrationals right now is pi. It's pi. So, but we're going to focus right now. Pi is not a irrational number, but these are all real numbers. Okay. So in our sets and subsets of rational numbers, we have rational numbers, and inside of rational numbers, we have, what's the next level? Integers. And inside of integers, we have whole numbers. And then we have the most narrow subset is counting numbers. Okay. So, I think that's the last slide. Okay. So, the integers, whole numbers, counting numbers, these are all rational numbers. So counting numbers are the numbers you can actually count on your fingers. 1, 2, 3, 4. It starts at 1 and goes for infinity, but it's always wholes. Can't be a half, can't be 1.5 or 1 3/4 or 127 point something. It's got to be a whole. So 1, 2, 3, and so on. What's the whole numbers only adds one little thing. What is it? 0. Because you can't count 0 of something. It represents nothingness, but it's not a counting number. It's not a natural number. Counting numbers. Oh, I need to write natural. How am I doing right there, youngs? Y'all can see that okay? Okay, I'm gonna move out. I'm just gonna move into the rational numbers. Okay, whole numbers. So it's 0, 1, 2, 3, 4. Whole numbers is all natural with 0. Okay, integers are all of our whole numbers. They're all of our counting numbers. And what else? Jenna? Yes. Question. As high as you want to go. Same thing. As high as you want to go. I think when we get to integers, it'll make more sense. Yes, Lena. All whole numbers and their opposites. So it's all positive and negative whole numbers with 0. Integers, all positive and negative wholes. So what have we left out? Rational numbers. And what have we? Fractions of stuff, right? Pieces, not wholes. So these are amounts that while they're precise, they're not wholes. So you could have, think about like counting money. We would be precise, and whatever you counted would be exact. You could have like $4.25 or 4 1/4. It's just not a whole. you could owe money, right? You could owe $10.50. So you could have a negative. So this is all the fractions and decimals, things that are positive and negative, but they're not whole numbers, okay? Okay. So any questions about organizing this Venn diagram or using it the Venn diagram way? Okay. All right. Well, that's it on the Venn